Hi everyone, welcome back. In this video series, I'm going to talk about optics in the human eye. So I don't know if you noticed, but I normally don't wear glasses. I should, but I have them. And anyway, we're going to talk about glasses, so I figured I'd wear them today. So more importantly, I'm going to talk about lens optics. So obviously I'm going to take a physics spin to how glasses work, how lenses work, how our eye sees images, and we're going to talk about corrections for those images. So I'm going to take those, still physics, a slightly different approach to this. So we'll talk about what refraction is, we'll talk about types of lenses, we'll talk about real versus virtual images, we'll talk about I'll do some calculations of lenses. They're pretty straightforward, so I'm not going to spend too much time on them, and talk about eye defects and how to correct for them. So this is all about the bending of light. So what happens is when light actually approaches a different media, it will go, especially if it's a thicker or more dense media, that light will bend. So that's the example of these glasses right here. So glasses work in that light comes into, like literally from the computer screen, the light comes into the onto the lens, and these are made out of I'm actually not entirely sure exactly the material, but let's just call them glass. So the light comes into the glass right here, but when it enters the glass, because it's more dense, the light actually bends, especially if it comes in at an angle. And what happens is the more dense that glass is, the more the light will bend. In fact, that's really important when it comes to glasses. We actually need that light to bend because for whatever reason, the light that's coming in and hitting our eyes is not hitting it in the right spot. So we call this property of light that bends when it hits a different media refraction. And basically, the more dense the material, the more bending. So we have our ray of light. You can see this little diagram right here. Actually, even better. I mean, I know you did this on a lab for most of you. I'm pretty sure you did this. But I'm still going to show you refraction. This is just a really good one. And I can do live what I want to show you. So here it is. Now we always measure the refraction angle from this thing called the normal. We're not going to do any calculations of this, although the calculations are not that challenging. It's called Snell's law. But notice that we have, let's set the angle that we go in at 30. Now notice how we measure the angle from this 0 point right here. So this is called the normal. So in other words, when the light is 100, right on that normal, notice that there's no bending of light. That's because it's going right through transmission right there. But it's when it's at an angle. And notice that we always start from here and work our way out. So notice that this is a measurement of 30 degrees. So this is not your typical protractor, right? You might have noticed that this would actually be at the 90. This would be at, what's 90? 110 or something like that, or 120, depending on what you're using. But anyway, the point is, notice that above in the air, so the medium we are in is air right here. And then right here, notice in the water, it's not going, in fact, it's not leaving at exactly 30. This is called the angle of refraction. In fact, it's less than 30. It's a little more than 30. It's like 22 degrees right here. So it turns out that if this was air, there would be no refraction. But as we get denser and denser and denser, notice that it goes toward the normal. So the more dense the material, the more it bends. What we're seeing here is the refraction of light, just like that. Now, like I said, that's what happens with lenses. But what happens is instead of one light beam, we have many. So our glasses capture lots of light. It's not just one ray of light. It captures light from literally anything it reflects, which is pretty much everything in this room. And now when it goes through the lens, because it is curved, it will bend differently. So this is called thin lens analysis. Now there's actually mathematics to describe thick lenses. I actually took an entire master's career to study optics, so I would say I'm a little versed in this. So we're oversimplifying things, which is fine. But the point is, once the light goes through the lens, it bends. And actually, technically, it does bend twice. And when it does, it's going to actually, on a more simplified view, either come to a focal point or spread out. So we have two types of lenses. Oh, there's not two. There's actually hundreds, depending on how you curve it. And we have double plano convex. There's a bunch. There's more than two. But like always, we start more simple. There are lenses that take all the rays that enter it and actually set it to a focal point called a converging lens. And then there's a diverging lens, which takes all the light and actually, literally, though I hate to use the word diverge, but diverges and actually spreads out. So it never actually technically comes to a focal point after the lens. Now, it actually theoretically does. If we trace those lines backwards, it actually does come to a focal point. So that's why I have a little asterisk there. But after the lens, you don't have any actual crossing of these lines. And this is just another way to kind of look at that. So when we talk about lenses, they make these things called images. So in other words, if we take a look over here, here's our lens right here. And this is what we call ray optics. Now, I'm not going to go in this course, I'm not going to teach the ray optics, the ray diagrams, all that fun stuff. I just want you to know the basics and just kind of see how lenses work. So what you're seeing is, actually I'm going to do it like this. So you see an object right here. This thing is called the object. And the thing that's over here is called the image. So notice that the image characteristics certainly change depending on where it is. In fact, I'll even do what is called virtual, like that, and like that. So what happens is when light passes through a lens, it makes an image. Now, for specifically, this is a converging lens. We actually have two types of images. We have a real image and a virtual. So a real image happens when you take your object, so the object's what's in front of the lens, and you place it behind the focal point. So notice that's the case here. In fact, we get magnification. So if you ever use a magnifying glass, it's most definitely, unless it's some other random one, a converging lens. But notice it's always behind the lens. This is a real image. Real images happen specifically when those rays cross. Notice that all these rays cross and come to a focal point. In fact, notice that it's actually the rays of the top of this. Technically, this thing is giving rays at all different locations, but again, we kind of simplify things. So when we do, all the rays at the top of this connect to here, and that tells us where the top of this is. So that's a real image. A virtual image happens when, I'll show you. So first of all, let me take this off. If you notice, if I bring it in front of, so this is called a focal point right here. So the focal point is where all the light, notice that the some of the light is going through that point. That's a focal point. That's a characteristic of the lens itself. So, so anyway, notice that when I do this, that this ray, and this ray would never meet. If we draw them infinitely, they don't cross. But what we can do is take those rays and draw it behind it. So notice these green lines. And they actually would meet, theoretically, behind the lens. And that's called a virtual image. So one real-life example of a virtual image is mirrors. Mirrors always make virtual images. In other words, notice that when you have a mirror, it's usually in front of a wall, right? And you know from experience that when you look in front of a mirror, you can't touch that image in there, right? You would touch the mirror. You're actually getting projection in your head, which is right. So what's happening is your brain actually redraws the lines in the back of your, in the back of your mind, and then interprets it as an image. So that's a virtual image. For converging lenses, it happens when you bring it in front, like this, of your focal point. And notice that we get a real image when we're behind the focal point. In front of the focal point, virtual, behind, real. Now, in the lab setting, you would actually be able to take a sheet of paper and put the image on here. That's the difference. If I asked you to do that with a virtual image, you wouldn't be able to because it doesn't exist. Notice that you wouldn't be able to, you could put that piece of paper behind that lens, but it doesn't happen. So there's some other things that are characteristics of these, of images created by lenses. One is, notice that it's upside down. This is called inverted. And notice this line right here, this blue line, right? So I actually could do this, right? Which is a little silly, but I could bring it down. But the point is that it's inverted, it's upside down. I can change the object to show you that any of the objects that I put here, I like arrows actually, is upside down. But notice that in this case, it's actually right side up. So this is upright, and this is inverted. Now, I'm always looking at this here. Notice I'm looking at the image right here. And then magnification. So about here, notice that these are relatively the same size, right? The heights are around the same. If I bring this back further away, this has a small height. So the magnification is less than 1. Once we calculate it, you'll see. And the magnification would be greater than 1 over here because notice that it is in fact a ratio of greater higher like that. So all images, all lenses can make types of images. So first of all, let me see, I just want to make sure I have it. Yeah, okay, good. So like I said, the virtual image is always an image that happens in front of the lens. It's actually not there. The real image happens behind the lens. So like I said, you can actually do this in lab. So HO is the height of the object. So the object's always in front. You can say that always in front of lens. And then the height of the image. So this is how tall it is. So literally this would be a measurement going back to our simulation, how tall this is. Now, notice the object keeps this, if I walk forward and backwards in front of a lens, I wouldn't change in height. But my projection would, right? What I see would change. So this is HO, object height, and this is HI, image height. The distance, so this is the distance from the object to the lens, the distance from the image. So distance right here. So we always treat this as a positive distance. So the distance from here to here is going to be, 9 meters. And then if the image distance is positive, it's a real image or in front. And if the image is negative, it means it's behind, it would be a virtual. So that's another unique thing like that. And then you have upright, inverted, and magnification. So to calculate these things, we use the thin lens equation. I kind of remember it as if I do, I die. This is just a little silly little thing that I remembered literally since high school, so it's worked for all these years. But what it does is it predicts an image distance based on the object distance and the focal point. Now, the focal point is defined by the type of lens. In fact, if you have a converging lens, that focal point has to be positive. And if you have a diverging lens, it has to be negative. So that's how this equation knows what kind of lens you use. And just like I said, if the image is a positive number, then it made a real image. And if the image is negative, then you have a virtual image. So it's a very, very powerful equation. We'll do an example, don't worry. And then same thing, is it real or virtual? Like I said, and then magnification. So magnification, this is the magnification equation, hi-ho, di-ho. Actually, I don't know why, there's always a typo in here and it annoys me. This negative actually should go here. Don't worry, I'm going to update these slides to reflect the changes that I make. Sometimes when I make my slides, I don't notice them. But when I talk about it, I do. That's better. The negative should go there. So if the magnification is around 1 or close to 1, then the object and the image are the same size. If the magnification is larger than 1, then the object is bigger. If the magnification is less than 1, it's smaller. And then if the magnification, fun other fact, doesn't say it here, if magnification is positive, then the image is upright. And if the magnification is negative, then the image is inverted. So there's so much information just based on these two equations. Oh, I have it right here. That's fine. And I have it right here. So that's good to know that one of my equations came out right. Let's make that nice and big. So it just looks better like that. Okay, let's try one out. Okay, this thing shut itself off. It's been too long, right? I'm just waiting for it to come on. There we go, there we go. So we have a 1 centimeter tall object that's 65 centimeters in front of a converging lens that has a focal length of that. Calculate the image position and its height. Oops, I'm not ready for that just yet. All right, so essentially we're going to be using the if I do I die equation. Oops. So as I look at this, one thing I do have to, I look for is what kind of lens is that? Because that tells me the sign of this. Converging lens means the focal point is going to be a positive number. So I found the focal length. And just for funsies, I'm going to make that positive. Now we have the height of the object. So this is the object height. So that's HO. This is always positive. And then we have the object distance, right? So this is a DO. It's in front of a lens. Usually, well, this is always positive, so that's good news too. Now, since these are all in centimeters, we can keep everything in centimeters. We don't need to convert to meters unless the problem specifically says that. So let's go ahead and calculate this. So it's 1 over 30 positive because it's a positive converging lens. If I do I, so then die. So di is what we're solving for. So that's the setup. Now, because of the inverting stuff, I like to use my technique. So I basically write it like this. I do the inverse of this instead of doing the 1 over. Because things just get ugly real quick. So basically, I have to subtract 65 inverted, subtract. Notice because I added here that I'm subtracting and not dividing, so that's a common mistake. So what this looks like then is 30 to the negative 1. So I'm just going to write this out. 30 to the negative 1 is this. Minus 65 to the negative 1. Around there. This is centimeters inverse, by the way. Sorry, I forgot my units. Would equal to this inverted. So now I'm going to go ahead and carry out that calculation. 0.0333 minus 0.015, 154. So this becomes 0.0179 centimeters inverse is equal to di inverse. So notice I have to inverse everything again to get rid of the inverse over here. So I'm just going to take the inverse of that number. I get 55.86 centimeters is equal to di. Just like that. Now this is very informative. The answer is positive, which means this is a real image. Spelled terribly, but you get the idea. Emerge. That's a real image. In fact, hopefully this is what it kind of looks like, right? So if I drew this really, really terribly right now, here's our lens, just like this. Our thin lens converging. Oh man, that's real bad. No, I can't have that. I have some standards. There we go. The object is a centimeter tall, so the focal point I'll put over here, which is 30, right? Now they're symmetric, so there's a focal point here at 30 as well. So this thing is 65 in front, so this is about right here. That's my object. So it's about here, but I don't know if it's inverted or not, so I'm not going to actually draw that part yet. So this is about 65 centimeters, but it's over here. But we can find that now. So even though the question didn't really ask me for this, I'm going to do it. Actually, I do have to do it because I have to find the height. So I'm going to use my magnification equation. So hi ho dido is what I'm going to use. Now, in order to find the height, I have the object height, but I don't have this or the magnification. But I do have these two numbers. So actually, I really do have two methods of solving this. One method is to actually ignore the magnification and set this up as a ratio. That's method one. Method two is to do it in 2 steps, where I find the magnification doing negative dido first, and then using that magnification, I could solve this. So actually, either of these do work. I am going to choose this method just to talk about magnification. I honestly would do it like this so I don't have to do extra work, but I'm going to do the extra work, like I said, just to show you how magnification works. So with that said, where are we? Yeah, so I'm going to do that first. So magnification, so step 1. So the negative sign is important. So negative di, which was 55.86 over the image. So we said that was what, 65? So let's go ahead and do it. So I get negative 0.859. And by the way, this is the centimeter, sorry, this is a centimeter, cancel out here, so there's no units for magnification. So this tells me 2 things. The fact that m is less than 1 means it's smaller. And the fact that m is negative means that it's inverted. It's upside down. So we have a real smaller inverted image. So now that I have that, I could use that number and set it equal to hi over ho, which was, 1 centimeter. So that's fun because that makes the answer pretty easy. Negative 0.859 centimeters. The negative of this, as you might guess, means it's inverted. So if I were to draw this, I'm going to draw it here because it'll just be nicer. I'm going to go ahead and use some skills here. So if I have my dotted line, there we go, beautiful. If not, that's okay, we won't say anything. And this is my lens. So that's my lens. So if my focal point's here at 30, the object was a little longer than 30, so it was about here. So I had the object as 1 centimeter, right, tall. This was 65. My image is going to be 55, so it's a little closer, inverted, and a little smaller. This was 50. 55.86 meters away, and the height of this was 0.859 centimeters. So there you go. That's how you solve the mathematics of this. The whole problem changes if this was a diverging lens, because then this would be negative. The human eye. Well, I'm not going to lie, I don't know too much more than what I have here about the human eye. Except for my calculations. That's the only calculation we'll do. Good news. Put this stuff away. Okay, so the human eye works. Basically, it's pretty awesome. It actually can actually the muscles, I think I think I read it that they I can't think of the word at the moment. They contract and relax to change the thickness of the lens, which therefore focuses light. So that's just amazing that your body does that. But there are many parts of the eye, but although everything's kind of listed here, I really want to really just address two things. In order to see, you need to get most of the light at the back of the eye, but specifically where there's lots of sensitivity, which is called the fovea. Now, in order to get the light to hit this spot, you need this lens, and that's what I particularly care about in terms of talking about, physics. So naturally, because of the way light bends, it doesn't mean that all the light actually gets to here. Sometimes the light will go past the fovea, never focus, and sometimes it'll go in front of the fovea. And this is where you have those issues. So look at the lens here. So notice that the lens can change to focus that light to that back spot right there. So I love this image because it shows you that. It shows you the change of the lens as you do that. So normal distant vision, so light coming in from very far away, your eye kind of relaxes. Actually, I don't know if it relaxes or contracts to make this, but it does something to cause the light to hit that back. And then same thing right here. Notice that if you're close up, the lens has to change so it comes back here. Oh, this is a really cool thing that you could do. You don't have to do it now, but there's a blind spot, and oh, I found it. Oh, that's so weird. I did it right here. So if you sit about, I'm about, I don't know, maybe a foot or two in front of my computer screen, and you close your right eye. If you move forward, you'll see the dot, but you'll move backwards, and the dot goes away. And that's your blind spot. There it is. It's so bizarre. No, it's like here-ish. There it is. That's my blind spot. Oh, it's kind of cool. You should do it. It just said. Actually, although it says your left eye, well, you could do either way, actually. It doesn't matter your right or your left eye. It works. We talked about this in the previous lecture. I'm talking about the rods and cones. The cones are the light, but the rods are sensitivity, how much light you're getting. But anyway, let's go back to this. So we'll get the defects. So you have two different types of defects. Farsightedness means you're good at seeing far away, but not up close. So what happens is that the light focuses behind your eye. Okay, so notice that this was what happened. So how do you do that? You need the light to come closer. So use a converging lens to do that. Your cornea is too flat. Your eyeball's too short. So one of these or both. But you use a converging lens to fix that. So one way you can tell, as I wore my glasses, I don't think you could tell. Oh, see how my face gets a little bigger, but not by much. If this were a converging lens, you would actually see my face get really big. In fact, let's see, my face should actually appear smaller if I put the lens up. And it does. See how my face is smaller? It looks silly. This is a diverging lens, actually, characteristic. We'll talk about that. So here's just another image of the, no, I'm sorry. This is nearsightedness. This is what I am. So nearsighted happens when I can't see far away. So what happens is the light actually focuses in front of the back of the eye. So I need something to make the lens kind of expand a little bit so that my already super concave lens, converging lens, can actually focus it to the right spot. So that's a diverging lens. So that's me right now. So I have trouble seeing far away. And usually what I do in class is like a demonstration, especially if people wearing glasses, is I'll go, you are, just by looking at you, I could tell by looking at your eyes what kind of lens you have. Because if your eyes are smaller, that's a diverging lens. If your eyes are bigger, that's a converging lens. So I could actually tell pretty easily what kind of vision impairment you have. Not to be, accusing or anything, just to be silly. But it's a pretty cool little technique you could do with that. So these are just some images of exactly what I talk about with that. So here's a couple other things about vision. So astigmatism. So that's when the cornea is curved more than others. So you don't have like a perfectly spherical eye. I know when the doctor was talking to me, because I have astigmatism in my left eye, he's like, oh, it's kind of like a football shape. It's not like that nice curve that you want. And that's what I have there, or a barrel shape. So what happens is you need an asymmetric lens. So all it means is that you can't just use a converging lens. You have to have your lens curved slightly off so that it can fix the offset of your eye with that. Now, back in my day when I got contacts, you couldn't get contacts for astigmatism. So I did get them anyway, but he said that you would never have perfect vision with your contacts because of your astigmatism. But nowadays, the technology has gotten better to make personalized astigmatism correction for your contacts. At least some of my students have told me that. By the way, I spent many years seeing life like the right side here before I realized that's not how life is supposed to be seen, especially with astigmatism. Another really weird effect of astigmatism, if you have it, is if you're ever driving and you see like lines coming out of the lights, especially while you're driving, and I know that I'm going to sound like I'm crazy, but that's also a astigmatism feature. I don't have an image of that, but I saw it online, and it was like a meme, and it said like, wait, no, not everyone sees it this way, and I just like lost my mind too, because I was like, wait a second, what do you mean nobody else sees this? So actually, it's really true. I do see things like this right side when I don't have my glasses, and then of course, life is just a lot more clear when you have your glasses. So it's a pretty interesting thing. Oh, I do have it. Yes, I do have it. I'm so glad. I must have put it in because I saw this exact photo. Yeah, so this is what it looks like with astigmatism. And like I said, I didn't realize that people actually saw life like this and not like this. So that's another characteristic of astigmatism. Good go me. I'm glad I put that in there. So another defect in lens is called aberrations. That's what happens when the light doesn't focus to one point. So it turns out that most lenses are not perfect. So as you can see in the left, this is perfect with no aberration. And notice the difference here, right? There's several different focal points, which means you don't get a clear image. This is the bane of our existence in basically a lot of telescope imaging. Now, there's a lot of corrections that you can do, so that's a good news, but I don't know, no image, most telescopes you buy at the store have aberrations in them, and you can see things, but not to the clarity of scientific level, right? But at the scientific level, you do care about these things, so you want to account for that. So there's spherical aberration. So what happens is you have to use a combination of lens. So you kind of like fix them individually so that they all come together to do that. So it's not just one lens that works. You just have to use a bunch of different ones. So if you just say a bunch of different ones for spherical aberrations, that's correct, because it actually is very specific to what you're trying to use or what the aberrations are. So this is, again, so when I take images, when I took images with my master's degree of some point sources, so stars, they all look like this. And this is because you have spherical aberration. And you can see the difference between no aberration and spherical. You get that fuzzy effect, right? Most cameras don't have spherical aberration because you usually are pretty close, and you have pretty high quality cameras nowadays. But back in your day, this is how you used to see some of the light sources. So chromatic aberration is because what happens is as light refracts through a substance, the color of light refracts differently. So then you get different focal points. Notice that they cross at different places. So you get this kind of weird rainbowy effect. It's actually kind of cool looking, but maybe not good for, your scientific studies, right? You could, how thick is this? It's hard to tell when you have 3 different colors, right? So this is chromatic aberration. And then you could do this by a combination of lens, and then you can do it with different type of glass, because you can basically change, one glass will have a refraction to fix the blue light, and then the one to fix the red light, and etc. like that. Ooh, okay, that's it. Okay, so I hope you learned a lot about the eye and how lenses work. You got a brief, again, I always say this because it's just so true. I could spend way more time on lenses and go through much more detail on some of these concepts. But those are the main points, is that you have converging and diverging lenses. They make different images based on where you place the image, where it is relative to your focal point. Converging lenses always focus your light. Diverging lens expands your light. Diverging lenses always make virtual images. Converging lenses can make both virtual and real images, all depending on the location of the image. Images can be upright or they can be inverted, so they could be upside down, and they can be magnified or not, and they can become smaller. Like my glasses always will make a diverging virtual image that is always smaller. And then there's lots of ways that images don't come out perfect, so we use corrections. So I will have some multiple choice online and coming up with about how to correct for some of these features of the eye that you have defects in. So I hope you enjoyed this video. The next video will be all about nuclear physics, so we'll take a total different spin on physics. Have a good one.